At the recent Tandy Assembly conference, I had a chance to talk to Arthur Gleckler about his game that he wrote for the trs80 Model 1 and 3 called Weerd. And he said something that kind of intrigued me, that the graphics were drawn just using single pixel set routines, which is a bit unusual. So I was kind of curious to take a look at that. Now, he hasn't made the source code for Weerd available, but I think with my emulator trs80gp, we should be able to find it fairly easily. So let's give that a try. First thing is we'll get a copy of trs80gp. And so we just need to go to 48k.ca/trs80gp.html. Download that. And then we'll also need a copy of Weerd itself. Now, these Big 5 games have been released into the public domain, so we should be able to find them at Ira's trs80.com site. Just pop down to the software search and search for Weerd. Now, to find this, we're going to look at it under the Model 3. So I think we'll just download the Model 3 cassette version here. And we'll just unpack those things into the working directory. Okay. So that is a cassette image, and we could run trs80gp and hook it up as a cassette image, but it's easier just to let it load it directly, which it will work for most programs, especially games. We can just say trs80mp gp. Well, Model 3 is a default, but we'll specify it just to be explicit, and then we'll give it the cassette image. And there, up it comes. So we can just start a game by pressing 1. Now what we can do is two things here. There's a lot of different options for investigating what is actually going on in the program. And the one I'm going to use today is the Z80 profile. What this does is it keeps track of what the Z80 is doing and tells you how many times each instruction has been executed, how many cycles it took. The idea is that you can run it on your own program, so you can determine if where they're spending their time and where you might want to optimize it, or just generally learn about them. So we'll just start that for a little bit, and you'll see it flashes profile up here while it's doing that. And then we hit record and turn it off, at which point it'll ask us to save it. So we're just going to save it in our little working directory here. It's profile0.txt. And that's all we need to do with that for now, so let's close that down. So we should have profile0. So now look at profile0.txt in the text editor. Notepad will do the job. And attempt to sort of self-document, it actually explains what the columns and what each of this means. But this is basically a list of all the Z80 instructions that executed and their addresses. Now, the one thing we're interested here is this memory wait states column, which you can see is mostly zeros here. It turns out on the Model 3, when the processor accesses video memory, it may have to wait. It's quite likely it will have to wait and do that, and so it's a delay which we can measure in the emulator. Now, for a pixel set routine, it's going to have to access the screen, so chances are any place we see that's getting wait states is going to be a place where it's accessing memory. So we'll just sort of look down through. And actually here we've got a huge number of wait states. This block move instruction was executed 50,000 times, which is, I guess, about 50 screenfuls. And in fact, we can tell just looking at the code here, this is, it's copying 2DE, which is this 3C00, that's the address of the screen. So this is obviously copying to the screen. And that this return did 14 wait states, that's a trs80gp bug, so don't worry about that. And if I zip through here, I don't see any place else where wait states were being taken. So go back up to where it was. So, as usual in sort of reverse engineering, this is, your first surprise you get is that, well, the set routine doesn't operate on the screen directly, obviously, otherwise it would show up here. And in fact, this is a pretty familiar technique we see here, is that there's an off-screen buffer at 7419 hex. And so obviously the program is operating on that buffer, drawing the entire screen in the buffer, and then very quickly copying it onto screen. That means you won't see erases taking place, and it reduces the flicker and so on. So it's a pretty common technique that you'll see in these games. But the good news is that gives us a clue, because chances are the set routine is going to want to look at the start address of this off-screen buffer in order to actually do its drawing. So if we look for 7419, we'll probably see other graphics related things. So we'll just search for that. And we see there's one down here, another down here, and another here. So there's a few places that it appears. So I'll just search back up again. There's our load. No, that's the very first one. So chances are one of these things is actually the routine we're interested in. And if we look at this one, we see that in fact, it's actually clearing the screen. So this is what actually clears the off-screen buffer, fills it with 80 hex, which is the blank graphics character. Okay, oops, gotta search forward. This routine here, looks like it's another clear routine. Okay. This is doing some manipulation of it. Actually, I bet that it's putting BF, so it's probably whiting out the screen or something like that. This is quite a similar looking routine. This is a more complicated routine, but I think it's the one might be the one we're looking for. There's a couple of things you notice, and this is out of familiarity with writing such a routine, is you see there's this little loop here where it subtracts 3 and jumps back to 73.6 here and inks B and starts B with -1. So it's successively subtracting 3 from a number and incrementing a register, which is a simple divide by 3. And the trs80 graphics have 3 pixels per byte vertically. So one of the things you typically have to do is you have your y coordinate, you have to divide it by 3, which gives you the byte row that you need to get your graphics on. So I suspect that this is the set routine. There's a few other things we can see down here. Right at the very bottom, there's a set 0 of HL, which is going to set a particular bit pointing at the screen, presumably, or the off-screen buffer, I should say. So that's probably the one that actually is setting the pixel. And you can actually see this is at 7413, and here we're loading A with 7414, adding A with C, and putting it back again. So we're actually self-modifying this, which is a common thing you also see in set routines, is that they'll use the generic bit set instruction and then put in the actual bit number they want to set as a bit of self-modifying code. It's one way of tackling the problem. And if we look higher here, we maybe have the question as to how exactly we know the start of this routine. And here's the previous routine, so maybe this 7381 is part of it. So where's 73BF? Well, it skips forward. 73BF is maybe one to consider, because if it does a comparison, it goes to 73C7, so it's here's a comparison against 128. Here's a comparison against 48. So this is doing bounds checking on the X and Y, keeping it within the 0 to 128 or 127, 0 to 47 range. So I think this 73BF is probably the set routine. Now, one of the perils of looking at a disassembly and doing static analysis like this is that you can convince yourself of what the code does, but you can't be certain of what it really does. So we can run the emulator to verify that. So we just go back to our command here and fire it up. And what do we do? Press enter to go in here. Press 1 to start the game. What we'll do is we'll just go into the Z80 debugger and we'll stop it for a moment. Just remind ourselves, what was that address again? 73BF. Okay. So what we've got down here in the debugger is we can actually go and look at Z80 memory. So we can look at 73BF. And we see it's sort of probably the addresses we expect. Now there's a 7B there. Now the Z80 opcode for returning from a subroutine is C9. So we can just delete that, put in C9. Now we've stopped it from setting pixels using that routine. So is that actually going to be the one that does it? Well, if it is, then probably we'll see all of this stuff disappear. So let's hit go again. Oh, sure enough, we don't see it. And we see that somehow the setting pixel routine is crucial for the progression as it brings in your ship. So we'll stop this again. And we'll change that back to 7B. I hope that's what it was. We'll hit go. And I think we've got a problem since these pixels weren't set, this thing's not progressing. But it doesn't matter. That was just a way we could have gone back to it, getting it normal operation. But you know, when you're fooling around with a running engine, this is what happens. So there it is. That's definitely the routine that we're interested in. So now one can pour over this and learn from it. Or what you can do is you can work backwards and see who calls this routine and maybe discover how shapes are stored or other things about the program. There is one other thing of interest that I should perhaps mention here if we run it again. Besides that particular operation, there's also something that's called under the record menu, something called bus use. Now, bus use is like profile, but it's more tracking about what the program's doing and what it's doing with each particular memory location, and is a better tool for actually starting a disassembly of something. And when we load a program from the command line, bus use knows that those bytes we loaded were kind of special, and so we'll treat them a little bit differently. So again, we'll just get the game running. and now do a record bus use, and again it's flashing, letting us know that's happening. And then we can, when we turn it off, it will ask us to save bus use 0.txt. Drop out of the emulator. Now we can look at this, and again it tries to document what was happening. So it actually noticed that there were 2 I/O ports that were used, or I guess 3. It says, oh, there were outputs to FF, which is a sound, so that's expected. EC, which is kind of a generic control. Not sure what it would be doing there. And also there was IO ins and port 0, which is the usual trs80 joystick port. So, and it actually is, it gives, defines for these things, equates, so we can kind of search them, so we can see, well, where, if we look for p_ec, we can find out where it was doing this. See here, it's actually putting a particular value out that port. Well, I don't know what that's about with a cursory examination. But again, there's a, what's different about this is that there is a whole set of markup it does here, where it's showing how this memory was accessed. And it will tell it if, it will actually be able to point out if it was self-modifying code, whether it was loaded by the emulator, i.e. specified on the command line, whether it was read or written or executed, whether it was the first byte of an opcode or the second or following bytes of an opcode, if you have a multi-byte opcode, whether it was the target of a jump, a JR, or a call or a return. If you're a target of a call, then you're actually a subroutine. Now, I can't actually remember what that routine was from the profile, so let's just go back here and remind ourselves that 7419, that's what I want to look for. So let's look for 7419 here. Right, I can just type F3, look, search forward. There it is. There's our set routine. So before, when we weren't quite sure about where the actual subroutine began, and we started a little bit into the subroutine just to be sure that we would hit it. But you can see here at 7318, this lowercase c means it was the target of a call instruction. So this 7381 is actually the start of the subroutine. And these labels here only appear when during the run of the program it detected that these addresses were referenced. So we can see that, you know, this was referenced, and then we can say how. Well, it was loaded by the program, it was executed, and it was an opcode fetch, and it was called. So these execute and opcode fetch instructions mean that, you know, this is actually part of the running code, whereas here you can see that we have bits of code where it was loaded and it was read and written. Although it says it was fetched, which doesn't seem exactly right to me, but I hope that's not a trs80gp bug, but it could be. The main thing I wanted to show you here is that we noticed before that it was self-modifying code, that this set 0 of HL is going to be changed to different bits as the routine runs. It figures out which bits it needs to set in a byte for a particular pixel, and it changes that. And so the bus trace marks that as self-modifying code, because that's the instruction it's modified, and it's actually the second byte of it, because this is a 2-byte opcode. You can see it here, CBC6. So it actually puts in the specific address here, 7414, which it equates to the last byte of the previous instruction. And we can see that this one is actually read and written, which is basically saying that if it's read, if it's executed, and it's written, then it's definitely self-modifying code. And so if we search for space M, we might find other self-modifying code or strings. How about if we search for semicolon space M? Nope. Typed that wrong. Okay, we'll go back. No, there's our set 0 HL. Nope, that's the only part in here. So for what executed while we had the bus use on, that's the only instruction we've seen where some self-modification took place, which is not surprising. It's a fairly uncommon technique. Now, one more cute thing you can do with trs80gp, which this code gives us a chance to look at. 7418 or 7419? I think it was 7419. Yeah, so at 4813, that's the one that copies the off-screen buffer onto the screen. So what that means is basically that's you know, the game does all its computations and it's going to copy that buffer and it's kind of done a single frame. And there's kind of an obscure trs80gp option we can pass that to, so we'll actually compute the frames per second. So we do, I believe it's FA, and that was 4813. If we run it, we'll see it's not saying anything up here in the status line yet, because this is probably not using the off-screen buffer copy. Now this is, and you can see that this is running at 9 frames per second up here in the title bar of trs80gp. And so if we actually start a game, and see we're running at 10 frames per second, 12, and it started jumping around. And so that's just a fun little thing to that if we can discover these locations in a program, that we can pass it in there and it will tell us about how fast the game runs in terms of frames per second, which is, you know, just yet another object of curiosity about how these games operate and how close they get to, you know, any certain speed and so on and so forth. So that's it. Learned a little bit about how Weerd works, and maybe a little bit about what trs80gp can do when it comes to reverse engineering. Bye for now.